Hello everyone. These are some of the practice problems we were going to do for physics. What you're looking at, this is my friend Dottie. She's needs attention all the time. And I devoted a camera just for her. And she's an adorable baby. Yeah. Oh, scritch. Alright, so we're going to do some problems. I'm taking them straight out of OpenStax, right? And so I'm going to try to do this. If there's any jump cuts, I know that's weird, but I'm going to try to do this where there's, we can look stuff up, we can read the text of the problem, we can see, the things that we want to do here, right? So, and then there's our paper. So this problem we're going to do, we're going to look at the Eiffel Tower. It's made out of steel. And we're going to give it a certain length. Alright, and so you want to draw a picture. The Eiffel Tower kind of looks like that, and has an observation deck, it has some antennas on top. Alright, and we're going to talk about its length, which is at some temperature 321 meters. Right? And that's at some temperature, right? Say the beginning of the day. Well, it's going to warm up, and when it warms up, we have to account for that, right? We have to account for the temperature change. Here in the problem, it's 15 degrees Celsius when it warms up. All right, so we're going to look for the thermal expansion of steel, and when I look that up, here, iron or steel. And its thermal expansion is 12 times 10 to the minus 6. Right? So alpha is 12 times 10 to the minus 6 per degree Celsius. Okay. So we'll do our calculation. We have one equation. It's plug and chug. All right, and we want our new length to equal alpha times L naught delta T. Delta L. We want the change in length. So this is how much extra height it will gain. And then we'll just put in what we have. So delta L is 12 times 10 to the minus 6 per degree Celsius. And then our original length is our 321 meters. And then we'll have our 15 degrees Celsius. You'll note those units cancel, and we're left with meters. We want a length, we got a length. And we do this calculation. I've done it ahead of time. I have a calculator here. We can note a few things. All right, this is going to be 10 to the minus 5, 10 to the minus 3, 10 to the minus 2. So we're expecting something on the order of centimeters, and that's what we get. Delta L will be about 5.78 centimeters, or 0.0578 meters. Right? One equation, plug and chug, linear expansion and volume expansion, similarly simple. Okay, our next problem, we're going to look at a volume expansion. Alright, so I got the new problem set up. This is a volume expansion. We're going to look at coolant overflowing out of a radiator. Right? So you've got your car. The car system, let's get a new sheet of paper here. Our new edge of paper. Alright, so the car system, alright, you have basically a sealed box. It's got 16 liters in it. And it's got an overflow. So the overflow spits out the side, and there's a little catch basin, which has to catch the stuff that overflows. So you fill this up at 10 degrees Celsius, and then this overflow occurs at 95 degrees Celsius. All right. And you're given the coefficient of thermal expansion here. Here we don't have to look it up. Beta is 400 times 10 to the minus 6 per degree Celsius. Now, this is a thing I want to note is in these formulas, well, two things. One thing is they're going to typically, these numbers are going to be times 10 to the minus 6 or 10 to the minus 3 because they're numbers for engineers, really. But the other thing is, note that the units that we have that go into it, the only unit that will go into this formula to start with is this degree Celsius. That's the one we know of. So if we put liters in, we'll get liters out. All right. And we don't have to do 1,000 liters equals 1 cubic meter. All right, because no one talks about anything in their car in terms of cubic meters. All right. So we're going to stick with liters. We're not going to convert that. And we're just going to go and say, well, our volume change, that's how much will overflow. All right, is that the liquid will take up more than 16 liters, but the space for it's only 16, so it overflows. It's going to be beta, our original volume, delta T. And we'll note that our delta T, right, it goes from 10 to 95, so it'll be 85 degrees Celsius. All right. And then we just put in what we know. Delta V is 400 times 10 to the minus 6 per degree Celsius. And then our original is 16 liters. And then our 85, you notice I'm now running out of space, degrees Celsius. All right, and we do our calculation. Again, I did this ahead of time, but we'll note that the degrees Celsius go away. And this is what I was talking about. Liters go in, liters come out. You match your units to whatever constants you have in the problem. Constants don't talk about distance, so we don't need them. And then our delta V ends up 0.544 liters. If you want an idea of how big that is, that's a 20-ounce soda. A 20-ounce soda poured out. When you have 30 some of them in your radiator, so that gives you kind of an idea of the expansion there. All right. So we're going to do some other problems, right? We've learned other stuff now with specific heat and calorimetry, and I'm going to get that set up. So we're going to pause for a minute. There's our poor little sleepy baby. Alright, so here's a problem. I'm going to work it out in front of you so we see how it works. We're going to do an identification with specific heat. And I want you to remember that our specific heat formula, right, it says calculate specific heat. We're going to use our heat, Q, is MC delta T. Now, what we're trying to find is C, so we want to rearrange this. Divide by M delta T, divide by M delta T. I'll get C by itself, and then we rearrange, and C will be Q over M delta T. My computer fan cuts on at apparently half CPU. I don't know why. That's interesting. All right. So now we can put in the things that we have in the problem. All right. Our heat is 4.35 kilojoules. All right. So C is 4350 joules. And we're using 1/4 of a kilogram, 0.25 kilograms. And it goes from 20 to 65 degrees Celsius. So 65 degrees Celsius minus 20 degrees Celsius is 45 degrees Celsius. And if you'll pause for a moment, this is the guy who interrupted the presentation. And if you think I'm going to let him waste 10 minutes of video, you're joking. And of course, my friend Dottie has had nothing to do with this. And we're back. Thank you, Pumpkin, for that insightful commentary. We're going to put in 45 degrees Celsius. All right, and then I have to actually grab the calculator and calculate what that number is. And of course, it fell on the floor. One moment. All right. You can't even see that. 4350. Thank you, Pumpkin. Divided by 0.25. Divided by 45. I get 387. Or if you'll... Pumpkin. He needs attention. He needs attention, and I'm going to give it to him. C equals 386.67. Note the units. Pumpkin. Joules per kilogram degrees Celsius. Alright, remember that number, 387. Alright, so we're going to avoid the camera and go look stuff up. Alright, so we go look stuff up. We want the specific heat. And the specific heat is in here. And we're looking for that table. And we're looking for something that's 387. And oh, look, it's copper. Alright, it's copper. Isn't that great? It is copper. So that's the one equation plug and chug, right? Is that we go and use one equation, we plug everything in. Now probably what you're remembering from, if you took chemistry, you're remembering calorimetry. You're remembering that you don't necessarily know how much energy is put in, and you're trying to figure it out. Here, it's nice because we knew this, and so it's one equation plug and chug. Potentially, you don't know that. So I'm going to pick a problem, and that's what we're going to go with. Well, I was going to pick a problem, but I got visited by my favorite panther, Spike. He's such a good boy. I'm still going to pick a problem, but I want you to see why sometimes I have a little bit of problems getting problems recorded and posted. So say bye, Spike.